Welcome to this video in our series on sorting procedures. This will be our final video and our final sorting procedure in this series. This will be a video on the quicksort algorithm. The quicksort algorithm is a very commonly used and well-known algorithm. And like our last algorithm, the merge sort algorithm, it also has a n log n runtime, at least according to its most common implementations. And so today I want to take a look at a simple implementation, again in Java. We'll take a close look at the implementation, see how it operates, and then I will conclude with a comment on its runtime. Once again, I've included here a Java implementation, again embodying my particular style of coding. And in this particular example, I want to take a look at, well, a couple steps here. Maybe at a high level, I want to first comment on the operation of quicksort and maybe contrast it with the merge sort algorithm that we just looked at. Very similarly to the merge sort algorithm, we're going to make two recursive calls. And these recursive calls are going to sort a sublist for us, and here we can see the sublist sort of operates the same way as it did in the merge sort. We have one list going from the start to some middle position, and then from that middle position to the end. These are both subarrays. We might call it the left and the right, if we will. The one distinction we'll see here after doing maybe an example or two is we're not guaranteed that these two subarrays are the same size, and that's going to be or even close in size necessarily, and that's going to complicate our analysis a little bit and also make the runtime of quicksort a little bit trickier to see. The rest of the operation here, the rest of what goes on in quicksort, is all carried out here, which we could break off and make it a subroutine. When we do break it off, we call it pivot. But what this operation is going to do for us here, and I'm going to look at it more closely, is what it's going to try and do is it's going to split all of the elements in our array into two, well, technically three sets. It's going to take all of the elements that are less than the pivot and put them to the left, and then take all the elements that are the right of the pivot and put them in the right segment, and the pivot here being one element privileged and selected to be a special element that we're calling the pivot. So we're going to use it. It's called the pivot because we're going to split all the other elements into those that are less than it and those that are greater than it. And in quicksort, one of the main options we have open to us is how we select our pivot. Which element are we going to use as our pivot? If we have no better way of selecting it, we typically select the first element to be our pivot, and that's what we've got here. So in this step, I'm selecting the start as the pivot, and we're going to use the starting element as the pivot. Now, I do want to kind of somewhat more closely look at this subroutine here, but maybe just to finish looking at the code here, that after we've pivoted our elements so that all the ones that are less than our pivot are to the left and all the ones that are greater are to the right, then we merely sort the left and sort the right recursively, and then all of our elements will be in the right location. So let's take a look at that again by looking at an example. Here I wanted to pull out an example where we look at how the pivot operation works, because my pivot subroutine is again a little bit peculiar. So to get us started here, I've got just an example array. I've got my start and my finish just clearly identified here in case we need to verify that. But to start out my code here, we're going to have two other variables that we're going to use. One here I've just got pp for pivot position, and then the other one here I, which is the index that we're going to use as we go. And we initialize both of these to start our loop out. So this is how the starting condition for our loop. Now what I want to do is I want to go through the loop and sort of verify what happens when we encounter values that are less than our pivot, and then also values that are greater than our pivot. So as we go, let's start out again here. Our start is pointing at 5. Our pivot is 5. We're going to just keep looking at the start location for our pivot. We're going to move the pivot position. It's not called pivot, it's called pivot position. It's going to keep track of where our pivot belongs, where it should go. And I is just going to keep track of which member we're currently looking at. But our pivot will stay in position 5 for the whole pivot in the first position here for the whole pivot operation. So we'll keep looking back at the start for our comparison. And we'll maybe see in our first line of code here inside our loop, we're going to compare if the element in position I is less than the pivot, which we're going to select by the one that's in position start. Well, obviously here I is not less than start, since they're pointing at the same one, they're equal, so we do not do the swap operation in this step. Instead, all that happens is we move our I to the next location. So moving our I here, now pointing here. Okay, in the next case, I've deliberately assigned the value that is less, so that now when we get to that if step, we know when we get to that if step, we're going to compare this position I to our pivot, which is position start. So is 2 less than 5? Indeed it is. So here's where we need to look at that swap operation. And now we need to be very careful, because what it actually does is it says what we want to do is we want to swap the element it says swap the element in pivot position with I, but we need to be careful here. It says plus pivot position. That means before we do the swap, we need to increment our pivot position. So after the increment, we're actually pointing at this pivot position, and then we carry out the swap. Well, swapping 2 with 2 doesn't do anything for us. And after this step, well, our I increments again. Okay, the next step again, we're going to compare our element in position I to the pivot position. And so element sorry, not the pivot position, the pivot itself, 5. 7 indeed is greater than 5. If it's greater than, we don't do anything except increment our I. And again, now we're at a case where we have a 4 in the location. 4 is less than 5. So again, we get a case where we are going to carry out the swap. Well, let's be careful again. The swap is going to swap the element in the pivot position with the element in position I, but only after we increase the pivot position, increment it. So we'll do a swap here. After the swap, we have the 4 in the pivot position, and the 7 has moved along. And now what we'll notice here is the 7 was actually greater than our pivot. So we need to make sure it's on the right-hand side. So as we add elements into our the left-hand side here, the 4 got added in. We had to swap it out and move it along. After the increment, we're now pointing at element 6, and element 6 is greater than 5, and so we don't do anything in that step, and so again that means incrementing our I. 8, same scenario, increment I again. Now our I is pointing at 3. 3 once again is less than our pivot, so we have to do our swap, and now hopefully we're getting familiar. We need to increment our pivot position first. Now it's back to pointing at that 7. Now we'll do our swap. Okay, we'll finish off with our next step or two. After the swap, we increment our I again. We notice that our I is pointing to this position now, 9. 9 is greater than 5. So the next step would be to increment our I again, and that of course terminates that loop. We'll notice after that loop, the very last thing we do is we swap the element that's in position 5, or sorry, in our start position, our pivot, with the element in pivot position. The reason it was called pivot position is that's the location that our pivot should be in. And now we can verify that these elements here, they're all less than the pivot. These elements here, they're all greater than the pivot. They're not necessarily in order. Neither of these sets are necessarily in order. But if we were now able to sort them, so this one would be our 2, 3, 4 if we sorted that set, and then we recursively sort this one, which would be 6, 7, 8, 9. Now we notice, aha, the whole thing is actually in order. And that's the basis of the quicksort algorithm, is that after this pivot position, if we just recursively sort the beginning and recursively sort the left and the right, then everything ends up being right in its right position. And so this is sort of an interesting characteristic of this algorithm, and maybe I'll draw a distinction here. In the merge sort algorithm, the first thing we did is we did some recursive calls, and then we did some extra work. That was the merge. Okay, so my extra work here is the merge operation. Now, in the quicksort algorithm, the very first thing we do is we do some extra work. That's my pivot, and then I do my recursive operation. And again, this is just to draw a distinction between these two algorithms. They both have to put in some extra work, and in fact, the extra work we put in is some linear amount of work, so some order n amount of work, and then we both have to do some recursive calls. And actually, both algorithms do 2 calls. There's one sort of benefit of the merge sort algorithm is we're guaranteed the size of each call is 1/2, or about 1/2, very close to 1/2, maybe greater than or less than by 1. But with quicksort, we're not guaranteed that. In this case, we kind of got lucky by design. I just put numbers in there that kind of pivoted well. But it was possible, depending on how we set this up, that our left-hand side could have no elements in it, or our right-hand side could have no elements in it, meaning that the recursive calls, in the worst case, one might be of size n-1, and the other one is of size 0, and that's the worst case. And so what that means is, and maybe I'll conclude with a quick sort of rundown here. So let's take a look at our final, our all 5 algorithms that we looked at in this video series. Usually when we categorize our sorting algorithms, we lump them into one of 2 categories, either the n-squared algorithms or the n-log n algorithms. You might think of those as the sort of the slower ones, the n-squared, or the faster ones, the n-log n. And so when selecting a sorting procedure, we have different rules for deciding which one we might want to choose. And so here I've sort of simplified some of the conclusions we've drawn in the last 5 videos. First, for our n-squared algorithms, bubble sort, insert, and selection sort, we have an n-squared worst case, and we argued in our 2 videos that both bubble sort and insertion sort are what we call adaptive, meaning in the best case, when you run them on almost sorted or already sorted input, they terminate early. So that gave them a good best case. That was not true of selection sort. Selection sort and merge sort operate in sort of a similar way, in the sense that no matter how the input is sorted, they will always carry out the same number of steps. So whereas bubble sort and insertion sort are adaptive, if you give them something sorted, they will do fewer steps. Selection sort and merge sort, no matter what the input is, will always carry out the same number of steps, with the possibility of doing fewer or less swaps. So when I say the same number of steps here, I mean same number of comparisons. And then the final algorithm we were looking at here was quicksort, and quicksort involved well, the problem with quicksort that means we're not going to do a detailed analysis in this video, is that the size of each call could be different. And if you get a real bad case, in fact, the best case scenario for bubble sort is give it a sorted list. Well, that's the worst case scenario for a quicksort, and you'll actually end up spending n-squared operations if you do that. And this is actually makes us think, well, why do we count quicksort as a n-log n algorithm? Well, actually, and I've sort of got it indicated here on my scribbles here, that the average case, so my AC here stands for average case. The average case of quicksort is actually n-log n, or if we actually use a different version of quicksort called randomized quicksort, where we randomly pick the pivot, it also has an expected worst case of n log n. And so for both of those reasons, we actually do count quicksort as a n log n algorithm. And also quicksort is commonly used in a lot of different programming languages in the base libraries as your standard sorting procedure. So a very commonly used algorithm. All right, I wanted to conclude this analysis of sorting procedures with a final comment about when we might want to use one procedure over the other. So here I sort of indicated, I've drawn two graphs here with maybe two different values, and here maybe I haven't stated, but there's probably some constants involved here, a cn squared and a dn log n, and there might even be additive constants in here, so we might have a plus 5 or something on here as well. And I've drawn it in this way so that we can see that depending on how these functions are written, and of course depending on some of the constants involved, there's going to be some location here where there's going to be a crossover. And this is typical of two algorithms where say we have a fairly simple algorithm like a bubble sort or an insertion sort, where the constant out front of our C here is fairly small, but its asymptotic growth time is n squared. Well, maybe for small values of n, because that constant out front isn't very high, we actually, this algorithm actually is quicker at coming to the solution than, say, maybe a merge sort that might have a larger, merge or quicksort might have a larger constant out front for the overhead, and they might have again an additive constant that boosts their algorithm up a little bit, or their runtime up a little bit. So when selecting an algorithm, just knowing that we have big O n squared or big O n log n, then that's not usually enough to decide which algorithm to select. What we also want to know now is, well, what is our value of n? What value of n are we talking about? Because if we're over here, we might want to use the n squared algorithm even though it's not asymptotically better performer. But then if we're out here when our n gets big, that's what the big O means, remember? When n gets big, this one is better. Okay, but maybe not for all values. Maybe for all values, but maybe not. And in practice, for our merge sorter and our quicksort, we might get better performance out of an n squared algorithm for n being small. Now, which value of n should we select? Well, I don't know. That depends on these constants, the c's and the d's, and whatever other constants are involved. And so it really depends on which which programming language you're operating in and what the purpose is. But I use sort of a rough line, and this is maybe not a great line to draw, but I've been drawing it for several years now. I've kind of picked this arbitrarily. 65,536, which is 2 to the 16, also known as 64K, 64 kilobytes. If your list is greater than this, I usually suggest using a merge sort or a quick sort. If it is less than this, I usually recommend just doing a bubble sort. And so for most of our purposes, this is going to be true. A bubble sort is probably fine. And certainly for a lot of your homework, you might have something that only has 100 elements in it. Well, yeah, a bubble sort is definitely going to be an efficient algorithm to run on a small list like that. In addition, when you actually implement these algorithms, both merge sort and quicksort, we do this recursion all the way down, and we kind of assume we stop when we get, we start at n, and we kind of assume we stop when we get to 1. But more likely, we're going to put some kind of line somewhere near here. Maybe it's not 2 to the 16, maybe that's pretty high. But in a merge sort algorithm, it's more common that we say, okay, hey, maybe we've got down to size 32 for our list. Let's just bubble sort that now. It's more efficient than splitting it into 2 again and 2 again and 2 again. And it gets even more ridiculous when we get down to something like 8. Well, we can probably really rapidly sort 8 without having to split it down to 4 and then split those 4s down to 2s. And then really, are we going to take a list of size 2 and split it down into 2 lists of size 1 so we can sort it? We only need one comparison to do that. So let's let's maybe save ourselves some overhead in doing recursion by cutting off that line a little bit earlier. So in implementation, a merge sort or a quick sort is more likely going to have at the base level a bubble sort or an insertion sort doing its brute force when our n gets small, and it only does its recursion at a high level. All right, I want to end this video now with just one last reflection, which is my analysis on quicksort and my analysis on merge sort is a little bit quick in these two videos, and I will indeed upload videos with a more detailed analysis, but that will be included in my other series on the design and analysis of algorithms, which goes into a little bit more detail and presents a little bit more of the mathematical tools that we need to analyze these algorithms. So if you're interested in that, please stay tuned. Those videos should be uploaded very soon. Otherwise, we'll continue in our next set of videos by looking at trees and tree structures. And so please stay tuned for that. Thanks, and I'll see you in the next video.